Ever look up and just see like a plane just cutting through the sky?
Yeah,
It looks effortless, right?
totally.
But behind that smooth image, there's this whole world of complexity.
Oh, yeah.
Aircraft design, it's not just about making things look cool.
Right.
It's a huge team effort.
Yeah,
All sorts of engineers tackling a ton of different factors.
absolutely.
If thinking about all that makes your head spin,
Yeah.
well, you're not alone.
That's kind of what we're here to unpack today.
Okay.
We're going to try to break down the core ideas behind how planes are designed.
Okay.
We'll focus on those early stages,
All right.
the conceptual phase, and we'll even look at some of the math that makes it all work.
Okay.
Like getting the blueprints without having to go through pages and pages of jargon.
Perfect. We've got these two really cool resources to help us out.
Okay.
First up are some excerpts from Aircraft Design.
All right.
It gives us a real inside look into how these huge projects actually get started. Then we're also going to tap into elementary linear algebra
Okay.
and get a feel for the math that underpins it all.
Sounds good.
So for you listening in, our goal is simple. We want to give you a clear and insightful look at those early design choices,
Okay.
how all these different pieces start to come together, all with the help of some elegant math.
Awesome.
So where does this incredible journey of actually building a plane begin?
Well, according to aircraft design, things really get going once a market specification is released.
So like a wish list?
Kinda.
Okay.
It outlines what potential customers need or want, or it identifies a gap in the market.
So a company or a group says, here's what we need this plane to do.
Right.
Then what?
That kicks off the conceptual study phase, which is also called the feasibility study.
Okay.
It's all about figuring out if this plane idea can actually fly, so to speak, in the real world.
Okay.
This phase has a bunch of important activities.
Right.
First, you have a deep market study analysis
Right.
to see how much demand there really is. Then engineers start coming up with different configurations,
Okay.
different shapes and layouts for the plane.
Makes sense.
They also look at what technologies they'll need to use.
Right.
And really importantly, they try to get a handle on the economics of the whole project.
Okay.
So it's a blend of market research, engineering, and money stuff right from the start.
It's like business meets creativity meets practicality.
Exactly.
Okay, so what are some of the specific things they do during this conceptual phase?
There are a few really important ones.
Okay.
Aircraft sizing. Figuring out how big it needs to be is key.
Right.
Engine matching, which means picking the right engine for the plane's performance goals.
Yeah.
And then preliminary weight estimation, trying to get an idea of how much the plane will weigh.
That seems pretty important.
Oh, it is.
Okay.
And even at this early stage, they start thinking about making different versions of the plane,
Okay.
like different payload capacities and ranges to attract different buyers.
So building in flexibility early on.
Exactly. It can save a lot of money and hassle down the road.
So kind of like building blocks that can be rearranged.
Yeah, that's a good way to put it.
Okay, so what's the big goal of this whole conceptual study?
The main thing is to choose a final design.
Okay.
But they don't do this in a vacuum.
Right.
They keep talking to potential customers all through this phase.
Makes sense.
It's back and forth, trying to find a design that balances everyone's needs
Okay.
and ultimately meets those crucial requirements.
Now, the book also talks about military aircraft design.
Yeah.
How is that different in this conceptual phase?
It's a totally different ballgame.
Okay.
Military planes are driven by national security needs.
Yeah.
They care about things like being better than the enemy's planes,
Right.
keeping the crew safe, and making sure the aircraft can survive in combat.
Of course.
They often start with something called technology demonstrators.
What are those?
They're kind of like experimental planes to try out new ideas.
Oh.
These demonstrators can then evolve into real prototypes.
Okay.
Cost is still a factor, but the main goal is meeting those specific defense needs.
Right. Not necessarily like satisfying a broad market.
Exactly.
So once they have a basic idea, how do they start thinking about the actual shape of the plane?
That brings us to aircraft classification or configuration choices.
Okay.
The book talks about civilian and military planes separately
Right.
because what they need to do is so different.
Makes sense.
Knowing what kind of plane it is,
Yeah.
a passenger jet or a cargo plane or a fighter jet,
Yeah.
and where it's going to be flying are super important.
Okay, so for a civilian plane, what defines its mission?
It mostly comes down to payload range capability,
Meaning?
how much it can carry people or cargo,
Right.
and how far it needs to go.
Okay.
The book even mentions stats for existing subsonic jets to give an idea of typical sizes for different needs.
Interesting. Now, one thing that seems simple but is probably really important is the weight of the plane.
Oh, absolutely.
How do they figure that out in these early stages?
It's called mass estimation,
Huh.
and it's crucial throughout the whole process.
Okay.
In these early phases, they use quick methods and even graphs for civilian planes to get an initial idea of the weight.
So those are like rough estimates.
Yeah.
Okay. Are there more precise methods they use later on?
Definitely, they have these things called semi-empirical equation methods.
Okay.
They use historical data from existing planes to estimate the weight of different parts of a new plane.
So they break it down into sections.
Exactly. The fuselage, the wing, the tail,
Yeah.
the engine, housing, the landing gear, and even all the little bits and pieces.
Okay.
These equations look at how the size and characteristics of older planes relate to the weight of their parts.
So it's all about learning from what's been done before.
Exactly.
Now, does the book give us any idea of how much each part typically weighs?
Yeah, it talks about mass fraction ranges.
Okay.
For example, the ratio of the empty weight of the plane to its maximum takeoff weight changes depending on the type of plane. Small piston planes, agricultural aircraft, small twin-engine planes, and business jets.
So it gives them a kind of comparison point.
Right.
And what about the materials they use to build the plane?
Oh, that's huge.
Yeah.
The book talks about how composite materials are being used more and more.
Okay.
They say for civilian planes, composites might make up like 10 to 15% of the empty weight.
Okay.
And for military planes, it's even higher, like 15 to 25%.
Wow.
And that number could go up even more as material science gets better.
So these lighter but strong materials are key for making planes more fuel efficient.
Totally. And they can improve performance in other ways too.
Now let's talk about the forces that actually make a plane fly.
Okay.
Let's dive into aerodynamics, specifically lift and drag.
Right.
So the book explains that lift, which is the force that counteracts gravity, comes mainly from the wings.
Right.
And it has a lot to do with the shape of the airfoil.
The airfoil, yeah, that's that curved cross-section of the wing.
Oh.
Think of the top surface of the wing being more curved than the bottom.
Okay.
That curvature is called camber.
Got it.
The other big factor is the angle of attack,
Which is?
the angle between the wing and the oncoming air.
Okay.
But there's a limit. If the angle gets too steep, the smooth airflow over the wing can break down and you lose lift.
That sounds bad.
It is. It's called a stall.
So it's not just the shape of the cross-section, but the whole wing design that matters.
Exactly. Wing aerodynamics also depends on the planform,
Which is?
the shape of the wing when you look at it from above,
Okay.
and its size, especially its surface area.
Right.
These factors have a big impact on how efficiently the plane generates lift and minimizes drag.
Okay.
The book also talks about wingtip vortices.
What are those?
Imagine the high-pressure air under the wing trying to get to the low-pressure area above at the wingtip.
Okay.
It creates these little swirling tornadoes of air.
Wow.
These vortices create induced drag on a three-dimensional wing.
So drag is basically the force that's working against the plane.
Right, it's the resistance it encounters moving through the air.
Okay. What are the main types of drag?
The book says there are two main kinds,
Okay.
parasite drag and induced drag.
So what's parasite drag?
It's kind of like the friction of the air against the plane's surfaces.
Right.
That's called skin friction drag.
Okay.
And there's also resistance caused by the plane's shape as it pushes through the air.
Okay.
It's called pressure drag.
Got it.
This type of drag doesn't really help with lift, and it has a minimum value called CDP-min or CD0.
Okay.
Induced drag, like we just talked about, comes from generating lift,
So you can't have one without the other.
pretty much.
Okay.
The total drag is just these two added together.
Makes sense. Okay, let's actually talk about the parts of a plane,
Sure.
starting with the fuselage.
All right.
The book mentions the fuselage fineness ratio.
Yeah, that basically describes how long and skinny the fuselage is.
Okay.
You take its length and divide it by its diameter.
Got it.
For typical civilian planes, that ratio is somewhere between 7 and 14.
Okay.
The width of the fuselage mostly depends on how many passengers it needs to carry.
Yeah.
And how the seats are arranged.
Right.
Like a single aisle with fewer seats across, or a wider double aisle.
Okay, so then we have the wings.
Yeah, the stars of the show.
The things that make it all possible.
Exactly.
How do they figure out the size of the wings early on?
They start with the wing reference area,
Okay.
which is called SW,
Okay.
and they estimate that based on the maximum takeoff weight
Right.
and how much the plane needs to carry and how far it needs to go.
Okay.
The book says this is just a starting point.
Okay.
They get more precise later on.
Makes sense.
They also mention other important things about the wings, like aspect ratio.
Which is?
It's the ratio of the wing stand tip to tip
Right.
to the wing's average width.
Okay.
And there's also wing sweep, how far back the wings are angled, and taper ratio,
Right.
the ratio of the wingtip width to the root width where it connects to the plane,
Okay.
and dihedral, the upward angle of the wings,
All right.
and twist.
Okay, so those are all connected.
Yeah, they all play a part, especially when you're trying to make a plane that can fly fast.
Okay, what about the tail section?
The empennage.
Right.
What's its main job? It's
Mm.
all about stability and control.
Okay.
The main things that determine its size are the length of the fuselage,
Okay.
the size of the wings, and the tail arms.
Tail arms.
Yeah.
What are those?
The distances from the plane's center of gravity to the horizontal and vertical parts of the tail.
Okay.
They're often called LHT and LVT.
All right.
To do initial estimations, engineers use something called the tail volume coefficient.
Okay.
It's a way to relate the size of the tail to the overall size of the plane.
Okay, are there different tail designs?
Yeah, the book talks about H-tails and V-tails. It also mentions things like putting a T-tail up high so it doesn't get hit by the turbulent air behind the wings.
Right.
It's called the wing wake,
Okay.
especially when the plane is at a steep angle.
So what about the landing gear?
The undercarriage.
Right.
What's important about that in the early design phase?
Yeah.
The most important thing at this point is figuring out where the landing gear goes in relation to the plane's center of gravity,
Okay.
the CG.
Right, the CJ.
Once they have a basic design, they decide on the landing gear layout.
Okay.
The book says the most common type is the nose wheel tricycle undercarriage.
Okay.
2 main wheels and a smaller wheel at the front.
Right.
Then there's the tail wheel type, which isn't as common anymore.
Okay.
They also talk about how they calculate the loads on the wheels based on the CG position
Right.
and the forces the plane experiences when it lands.
Makes sense.
The tires and shock absorbers need to be able to soak up a lot of energy during landing.
Right.
And there are limits on how fast the plane can descend to make sure it touches down safely.
Okay, so last but not least, let's talk about the engine housing.
The nacelle and intake.
Right.
So a nacelle is basically the streamlined shell that goes around the engine.
Okay.
In civilian planes, the engines are usually mounted outside on pods or pylons,
Okay.
often under the wings or sometimes at the back of the fuselage.
Okay.
But military planes often have their engines inside the fuselage.
Okay.
Designing the shape of the nacelle, both inside and out, is important for smooth airflow
Right.
and minimizing drag.
Makes sense.
And things like ground clearance need to be considered too.
Yeah, I've noticed that some planes, like the Boeing 737, have those kind of flattened bottoms on their engine housings.
Exactly. That's to make sure they don't scrape the ground.
So we've talked about the physical parts, but how do they know if this plane will actually do what it's supposed to do?
Performance.
Exactly. How do they test that out?
The book mentions the VN diagram. It's a graph that shows the relationship between the plane's speed,
Okay.
V, and the load factor.
Which is?
Basically, how much force is on the plane compared to its weight,
Okay.
mostly from lift.
Yeah.
This diagram is super important for defining the safe operating limits of the plane.
So like how fast it can go and how much stress it can handle.
Yeah, exactly.
Oh, okay.
They also talk about takeoff and landing distances
Right.
and all the things that affect them, like flap settings, drag, and friction between the tires and the runway.
Makes sense. What about climbing and cruising speed?
Climb performance is a big deal, too.
Yeah.
They calculate the rate of climb.
So how fast it can gain altitude.
Exactly.
Okay.
And the book says that the plane's acceleration during climb affects this because some of the engine power goes into speeding up instead of just going up.
Makes sense.
Then they talk about the maximum cruising speed and how much thrust the engines need to get there and stay there efficiently.
So it's not just about getting from point A to point B, but doing it smoothly and efficiently.
Right.
Of course, a plane also needs to be stable and controllable in the air.
Totally.
How do they design for that?
Like we said before, the tail section plays a big role in stability and control.
Right.
The tail volume coefficients help them figure out how big the tail surfaces need to be.
Okay.
The book also mentions 4 basic ways a plane can move if something disturbs it.
Like what?
Directional divergence, where the nose keeps moving off course.
Okay.
Dutch roll, which is a mix of yawing and rolling.
Okay.
Spiral divergence, where the plane goes into a tightening spiral.
Yikes.
And phugoid oscillation, which is a slow up and down motion.
Okay.
They talk specifically about directional divergence and how a V-tail can help prevent it.
Interesting. So the overall layout and how the weight is distributed also affects stability, right?
Oh, definitely.
Huh?
The position of the center of gravity is super important,
Right.
both for stability in the air and on the ground.
Okay.
The book also says that where the wings are attached high or low, and whether the wings are angled up, dihedral,
Right.
or down enanhedral.
Okay.
can also change how stable the plane is.
So many factors to think about.
There are.
What about the actual control systems?
Oh, yeah, they mentioned fly-by-wire systems, FPW.
Okay.
Those use electronic signals instead of mechanical links to control the plane.
Okay.
They can make the plane more stable and
Ah.
easier to control.
Interesting. Of course, we can't forget about cost.
True money makes the world go round.
It does.
So how do they factor cost into the design process? It's a big deal from the very beginning.
Okay.
The book says that cost is looked at differently for civilian and military planes.
Right.
Civilian planes need to make money by carrying passengers and cargo,
Yeah.
but military planes are usually bought by just one customer, the government.
So different financial goals.
Exactly.
What are the main cost factors for each?
For civilian planes, the big thing is direct operating cost, DOC.
What does that include?
Things like fuel maintenance crew salaries and airport fees. They say indirect operational costs like administration are usually dealt with separately.
Okay.
For military planes, it's more about life cycle cost, LCC.
Which means?
All the costs from development through its whole life, even disposal,
Okay, so from cradle to grave.
pretty much.
What about the actual manufacturing costs?
The book breaks that down into a few main parts.
Okay.
Cost of materials, cost of making the parts, cost of assembling the plane,
Okay.
cost of support activities like quality control,
Right.
and the cost of those initial research and development expenses.
Okay.
Plus all the other little costs that pop up.
So many moving pieces. Now, we also promised to talk about the math behind all this.
Right, the linear algebra connections.
Exactly. So where does linear algebra fit in?
The aircraft design excerpts don't really get into the equations themselves,
Okay.
but linear algebra is like the hidden framework that supports all the engineering calculations.
So it's working behind the scenes.
Exactly.
Can you give us some examples of how it's used?
Systems of linear equations are super important for things like structural analysis.
Okay.
Engineers use them to figure out how much stress the plane's frame can handle.
Right.
They're also crucial in aerodynamics,
Okay.
like in panel methods,
Okay.
which are ways to analyze how air flows around complex shapes.
Right.
And they're also key in designing control systems
Okay.
to see how the plane reacts to the pilot's inputs and things like wind gusts.
So these linear algebra excerpts actually show how to solve these systems.
Yeah, they give you a taste of it.
Cool. The linear algebra book also talks about vectors.
Right.
How are those used in designing planes?
Vectors are a great way to represent things like forces and movement.
Okay.
Lift, drag, thrust, weight.
Yeah,
Those can all be represented as vectors with a size and a direction.
makes sense.
The plane's speed, acceleration, and even its position and orientation can be described with vectors too.
Okay, so what about matrices?
Matrices are really useful for representing transformations in the plane's geometry.
Like what?
Like if you need to rotate a part or scale it up or down, you can use matrices for that.
Okay.
They're also a really organized way to work with those systems of linear equations.
Okay, finally, the book talks about eigenvalues and eigenvectors.
Right.
Do those have any practical use in aircraft design?
They do, even though you won't see them in the early sketches.
Okay.
Eigenvalues and eigenvectors are important for understanding how stable the plane is and how it vibrates.
Okay.
Think of eigenvectors as showing the natural ways the plane's structure can vibrate.
Okay.
By finding those early on, engineers can design the plane to avoid really bad vibrations.
Okay.
Those could cause it to break apart.
Right.
Eigenvalues can also tell us how stable the plane is overall.
Meaning?
Will it return to a stable state after a gust of wind, or will it keep wobbling?
Got it.
So even though these linear algebra concepts might seem abstract, they're super important for making sure the plane is safe and flies the way it's supposed to.
So as we wrap up, what are the big takeaways you'd want our listeners to remember about these early stages of aircraft design?
Well, we've seen that it's a really complicated process.
Definitely.
There's a lot of back and forth between market needs, aerodynamics, weight distribution,
Yeah.
the shape and layout of all the parts, making sure the plane will perform well, stability control, and of course cost.
Right, it's all connected.
Exactly.
And it's important to remember this was just a high-level overview.
Oh, yeah.
Each of these areas has tons of details that we could spend hours talking about.
Absolutely.
So to leave you with something to think about,
Okay.
we talked about all these different factors that go into designing a plane: market demand, technology, economics, safety, regulations.
Right.
Which one do you think has had the biggest impact on how planes have evolved over time?
That's a good question.
Yeah, something to ponder. And if you're interested in learning more, we encourage you to dig deeper.
Definitely.
You could look into the history of specific planes.
Yeah.
or see how different wing shapes affect aerodynamics.
Right.
Or maybe even dive into the world of modern flight control systems.
There's a whole world out there to explore.
We hope this deep dive has given you a new appreciation for the amazing and complex world of aircraft design.
Thanks for joining us.
Thanks for listening.